All right, here's example 3.7 from OpenStax PreCalculus. I was going to skip this example and just do the try it on dividing complex numbers because I figure that one, the answer is not provided for you. But I didn't find one that was just dividing complex numbers. So I decided I'd actually work through this example. So really I'm going to end up talking through most of this, but what are you going to do? Divide these two numbers. To divide complex numbers, what you need to know is, or what you need to do, I guess, what I like to do, I guess, is I like to write this first as a fraction. Right? Divide this by this. Well, that means this right here. But writing it in fraction notation allows you to do some stuff. The first thing that it allows you to do is take advantage of the fact that if you have a fraction, any fraction you want, like 1/2 for example, and you feel like multiplying the top by 3 and the bottom by 3, you get something that's equal. 3/6 is the same as 1/2. And the reason these two numbers are the same is because I chose to multiply the top and the bottom by 3. And multiplying the top and the bottom of a fraction by a given number does not change the value of that fraction. That same logic applies here. I can multiply the top and the bottom by a number if I felt like it. If I felt like multiplying the top and the bottom by 7, I should feel free. That will not change the value of this fraction. But I don't want to multiply the top and the bottom by 7 because that's not going to help at all. In fact, no, that's not true. I was going to say there's only one thing. That's not true. There's infinitely many things that I can multiply the top and the bottom by to help to get rid of the I on the bottom. But the one that I'm going to choose is the complex conjugate. So I said a lot of stuff there. First off, what you need to know is first, write your problem as a fraction. Then multiply the top and the bottom of that fraction. And note that by doing so, you're not changing the value of the fraction by the conjugate of the denominator. So always by the conjugate of what's on the bottom. Why do you do that? It turns out that when you multiply by the conjugate, you always get rid of the imaginary part. It turns out that this times this will be a real number. And nothing special with the 4 and the I, just anytime you multiply by a complex conjugate, that always happens. And why is that good? Well, because I want to write this in standard form, a plus bi, something that looks like one of these guys. And a plus bi doesn't have any i's in the denominator. So really my goal when I'm dividing complex numbers is to find something that's equivalent to this thing in red that doesn't have any i's in the denominator. And the way you do that is you multiply by the complex conjugate. So let's do it. I don't know if the color even matters, but I'm going to make this in red to show that it's equal to this. Multiplying complex numbers, I can do that. I learned that a couple examples above. It's kind of like, well, if you do the books way, you sort of memorize what pieces go where. If you do it more the way I like to do it, or kind of what they refer to here, you can sort of think about it as FOIL. 2 times 4 is 8. 2 times I is 2i. 4 times 5i is 20i. And 5i times I is 5i squared. And I'll simplify that, but before I do, since I'm thinking about multiplying polynomials right now, I'm going to multiply out the bottom. 4 times 4 is 16. 4 times I is 4i. However, this 4 times this negative I is negative 4i. Oh, how convenient. Right, this 4i and this negative 4i cancel each other out. That will always happen anytime you're multiplying by the complex conjugate. Maybe you can convince yourself of that. The outer and the inner will always be the exact same, except one will be negative and one will be positive. Negative I times positive I, be a little bit careful here. A negative times a positive is a negative, and I times I is I squared. So I get here. On the top, plus 5i squared is the same as plus 5 times negative 1. And 5 times negative 1 is negative 5. So really, this whole thing is negative 5. And the 8 and the negative 5 combine together to give me 3. And the 2i and the 20i combine together to give me 22i. Down in the denominator here, I'm hoping this whole thing ends up being a real number. If I did things correctly, that should always happen anytime I multiply a number by its complex conjugate. Let's see if it works out. Well, 4i and negative 4i, those cancel out. Negative I squared is negative negative 1, aka positive 1. So I got 16 plus 1, I just got 17. And you're really happy when you get here, but technically you're not done. And this is getting really nitpicky. This right here is not a complex number because it's not in the form a plus bi. To get it in the form a plus bi, I have to algebraically manipulate it a tiny bit. If you wrote this, I'd know what you mean and I'd be pretty happy with your answer. However, the quotient of two complex numbers, when you divide two of them, it should be a complex number, so we're not done here. Instead, we say, well, this is 3/17 plus 22/17 I. Notice now it's a plus bi. And if you're not sure that this is equal to this, well, 22/17 times I, you could think about that as 22/17 times I over 1. So the I would go up on the top. What I'm saying is this right here is 22I divided by 17. And if you had 22I divided by 17 and 3 divided by 17, you could add those together because you'd have a common denominator. And when you're adding fractions with the common denominator, you add the numbers up on top, you get 3 plus 22I, and then write the denominator one time to get this 17. This right here ends up being the answer in a plus bi form. So I'll end this video here.